But till now only 12 students joined. It is very bad situation from BA as well as BB, because you should join 5 minutes earlier to actual lecture timing. It is very bad situation. I will not start until you cross 50 plus attendees, at least 50% attendance. Out of 136, only 13 students joined till now. And there is a message from your previous lecture also. Only 48 students were present. That is informed to HOD madam as well as me. That is status of today's first lecture attendance. And yesterday also for DA lecture, there was around 60 students present, if you see there. And for my lecture also around 55 students were present, not more than that. So it is very bad situation. So I think in this week your attendance will be conveyed to your parents also, I think, because how many students are attending real-time lectures, and how many students are watching video lectures. Only 21 students yet as a attendee. Thirty students yet. Only 30 students are there. It is a very bad situation. I think hardly you have 3 lectures per day, not more than that, right? You must attend these all lectures. Just 33 students. Okay, from today onward, those students are joining 10 minutes late. I will make, or I will prepare the list of such students. If you see there, and we'll see the frequency of their joining, whether they are joining every day or each lecture on timing, or they are doing same delay. So we can say the list of such students will be prepared there. And few students are there, they are not joining for any one lecture. Their separate defaulters list will be prepared. still 34 students joined, 35 now. It is already 5 minutes over. That is, it is 11:35. Okay, at least I will take the recap. And today also you have second session of seminar or webinar. Okay, on career guidance. Guidance for the you can say the admission to MS, MTech or PhD abroad. You see that. So first section has conducted yesterday through YouTube channel, and today also there will be the second and final session. So I request you all attend that session compulsory, and those are interested in that is the MS MTech. If you see there, they can subscribe that channel, because we may not conduct or arrange same meetings in or seminars in future. So if you have subscription, you can watch those videos again. If you have any difficulty during your you can say the MS or MTech admission process, or for GRE and TOEFL, you can say the examination. Okay, so this is my suggestion. If possible, for such students, they can subscribe that channel. If you see there, that will be helpful for them only. Those are interested for MS and MTech abroad. If you see there, because they need to appear for GRE and TOEFL like examinations, so they will not face the problem. If you see there, okay. Anyway, till now 39 students joined only. I think madam will also join our session anytime. HOD madam, if you see there, and we'll see our actual strength. If you see, so how many students are there, madam will see those students also. If you see, because this message is conveyed to madam yesterday, and in today's first lecture also only 48 students were present. And in my lecture also, till now only 39 students are there. So it is very bad situation, if you see there. So you can please tell your friends join session as early as possible. If you see there, if you see these messages, yesterday's DA lecture only 65 students. Okay, so such type of messages are there. If you see there, this is very bad situation. If you see there. Recording. Anyway, am I audible to all? Only 42 students.
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, we'll start at least. We'll take the recap of the previous lecture, because in last lecture we already started the decomposition techniques. If you see there, so 4 types of main decomposition techniques are there, like the data decomposition, then recursive decomposition, exploratory decomposition, and one more is the speculative decomposition. So these 4 techniques are there. So we'll see these techniques one by one. I think out of them, recursive decomposition technique we have seen already in last lecture. So all of you are aware of this recursive decomposition. That is, it follows divide and conquer. You can say the algorithmic strategy for decomposing the task into you can say the number of subtasks, and those subtasks will be assigned to the you can say the different processors for the concurrent execution. So that kind of example we have already seen. That is the recursive decomposition by taking the example of the quicksort algorithm that is also discussed yesterday. And then another example we have seen to find the minimum element in a given list or the array. So in that case, we have seen two algorithms in the form of pseudo C code. If you see there, that is one for serial execution and another how we can convert same algorithm for the you can say the recursive search of the element in a given list of n elements. That is also discussed yesterday. And recursive decomposition, this is the quick sort we have seen already yesterday, no need to repeat. Then this is the serial execution to find the minimum element, and this is the recursive you can say the decomposition to find the minimum element in a given list. This is the recursive approach for the decomposition, if you see there. Then we have discussed about the actual example, that is the how recursive decomposition takes place there. Then moving towards the second
Sir?
type of, yes.
Hello. Sir, actually
Yes.
screen is not visible.
Screen is not visible. This is problem to all.
Yes, sir.
I guess so, sir.
Yes, sir.
Okay. Okay, let me see. Only I am audible to all, na?
Yes, sir.
Yes, sir.
Okay. Okay.
So you're audible.
Okay, okay. Recording is also going on, but sharing was stopped. That was the reason. Okay, now it is visible.
Yes,
Hello?
sir.
Okay, good. So already we have discussed okay, we are facing some problem. That's why it was stopped again. I need to share it. Can anybody tell me? Am I audible now?
Yes, sir.
Yes, sir. You are audible.
Yes, sir.
Okay. Recording is
Yes.
in progress.
Yes, sir.
Yes, sir. Recording is.
Okay, if recording stops because I left meeting and again rejoined meeting due to some problem. That is only reason. Okay, sharing is already done. I will okay. Now this slide is visible to all. Hello.
Yes, sir.
Okay, good. Thank you. Then moving towards the second type of data decomposition technique, data decomposition. If you see there, in previous lecture we have seen the recursive decomposition technique. If you see there, where you are applying the divide and conquer strategy to divide the given big problem or large problem into sub problem and sub problem into sub and sub problem likewise, till the sub problem itself is a solution or it is too small, it can be you can say computed easily if you see that. So in this way you are performing the recursive decomposition. We have already taken two examples. One is for the quick sort and another one is the, you can say, finding the minimum element from a given list of elements, n elements, if you see that. So this example we have already seen. Then moving toward the data decomposition. In data decomposition, if you see there, decomposition can be performed on at three different levels. If you see there might be the output data decomposition, there might be the input data decomposition, or there might be the intermediate data decomposition also, if you see there. So in case of the intermediate data decomposition will be series or sequence of sub computations there. If you see there, that is showing the different transformations. Those are performed during your computation, intermediate computations, if you see there. So what is data decomposition? If you see there, you need to identify the data on which computations are performed, and you have to partition that data across various tasks. Means you have to divide that data among the multiple tasks, and those tasks will be you can say are assigned to the, you can say, the particular process will have the collection of tasks, and that process will be executed on a particular processor. If you see that here, meaning of process is nothing but the either parallel algorithm or the parallel you can say the API or the parallel program. We already discussed yesterday meaning of the process in case of the our parallel programming, if you see that. Then or high performance computing. So this is nothing but the partitioning of the data is nothing but the decomposition of the problem, if you see there. And data can be partitioned in different ways, if you see that. So there may be more than one decomposition approaches you may have right now, because either you are you are carrying out decomposition on the input data or the output data, or that may be on an intermediate you can say decomposition you are performing there. So there are different approaches. So which terms you are considering first, or whether you are changing the sequence of terms, okay, while performing the computation, if you see there, or decomposition. So it will definitely affect the performance of your parallel algorithm, if you see there. So you have to select the approach, okay, which will not affect the or degrade the performance of your parallel algorithm, if you see there. That kind of approach you need to follow there. So moving towards the data decomposition, initially we'll see the output data decomposition. So what happens in case of the output data decomposition? Here each element of the output that can be computed independently of others, if you see there. So you have to select those elements, if you see the independent elements from which you will directly get the output, if you see there. These are not the input elements. So we'll take one example of the matrix multiplication, from which you will understand how actually the output data decomposition taking place and where it is taking place and how it is taking place, if you see there. So we'll see directly one example, output data decomposition, if you see that. So in current slide we have considered two matrices A and B. These are n by n matrices, but for sake of convenience we have taken that is the 2 by 2 matrix there, if you see that. And resultant matrix will be the C, if you see there. And this is nothing but the output matrix C, and this can be partitioned or decomposed into 4 tasks. That is the C11, C12, C21, and C22. If you see there, so task 1, 2, 3, and 4. These are the part of the output data here. So how you have decomposed your output into 4 number of tasks. So task 1 will be responsible, that is C11 equal to, that is nothing but the multiplication of first element of your first row with the first element of the first column of the second matrix, that A11 B11. Similarly, plus A12, that is second elements of the you can say the first row of the first matrix will be multiplied with the second element of the second row of the you can say the second matrix B21. If you see there, then you will get the output C11, that is the first element of the first row of the resultant matrix C. Similarly, C12, C21, C22 computation will be performed. So here you have to remember, if you are computing, that is your decomposition approach may be different there. If you see there, output decomposition, for example, I may assign task 1 C11 equal to A11 B11 only, and then I can perform second task as a again C11 equal to C11 plus A12 B21. So this is possible. So these are the different approaches you need to you can follow there for the output decomposition also, if you see there. So same example is given in next slide. See, output data decomposition example. For same example, there are two approaches, decomposition 1 and decomposition 2, if you see there. So if you see there, task 1, 2, and 7 and 8, these are same in both decomposition 1 and decomposition 2 in a current slide. But task 2, 3, 4, and 5, if you see there, their approaches are different. If you see there, that is nothing but the in case of the task number 3, C12 equal to A11 B12. So this term A11 into B12 has taken first there, and then in task number 4 in decomposition 1, that term is added, C12 equal to C12 plus A12 B22. But in case of the decomposition 2, task 3, that is the C12 equal to A12 B22, that is second term is considered here. Okay, for task 3, and that is considered for the task 4 equal as a C12 equal to C12 plus A11 B12. So it depends on your logic of the decomposition or which approach you are following there. So it definitely impact the performance, overall performance of your parallel algorithm, if you see there. So these are the two different approaches for output data decomposition for multiplication of you can say the two matrices A and B, if you see there. Similarly, if you see there, task number 5, C21 equal to A21 B11 in case of decomposition 1, whereas in case of decomposition 2, the task 5, C21 equal to A22 B21. So sequence is you can say sequence term is taken different, okay, into consideration, if you see that. But final result will be same, if you see that. Okay, so which approach you are following there, that does matter there, if you see there. So another example for output data decomposition, if you see there, here input is the data set of the transactions, if you see there. So there are total 10 data sets are taken into consideration. That is the first transaction having the sequence like A, B, C, D, A, B, C, E, F, A, B, C, E, G, H, and last one is the F, G, H, L. So this is the you can say the transaction input, and item sets are also input, whereas the frequency count will be the output in this example, if you see that. So which is the input data set here, that is nothing but transactions and the item sets, whereas the output is the frequency count, if you see there, or output data set, that is nothing but the frequency count. So you can perform the input decomposition on the transactions and the item sets, whereas the output decomposition is possible on the that is there item sets frequency count, if you see that. So in current example or current slide, we have partitioned the frequencies and item sets among the tasks, if you see that. So if you see there, task 1 and task 2 are shown here. So input data sets is common in both tasks. Okay, whereas the item sets are we can say divided on in task 1 and task 2. That is, the first 5 item sets are given for task 1, and the next 5 item sets are given to the task 2, if you see that. And accordingly their frequency in item set frequency count will change there, if you see that. That is, it will show only the frequency count for first 5 sorry, not 5, only we have taken the 4 item sets in case of task 1 and 4 item sets in case of the task 2. So this is one kind of you can say the decomposition. This is nothing but the this is the input decomposition, because you have, as well as the output decomposition, because you have performed here that is the decomposition considering the item set frequency count, that is divided into 2 sets. Okay, that is allocated to task 1 and task 2, 4 elements to task 1 and 4 to the task 2, if you see that. That's why frequency count of the ABC is 1, D 3, CFG 0, AE 2 in case of task 1, whereas in case of task 2 remaining item sets are considered, CD having frequency count 1, DK 2, BCF 0, CDK 0, likewise. Then okay, for your understanding, this slide again added regarding the previous example. So if the database of transactions is replicated across the processes, each task can be independently accomplished with no communication. Yeah, so in that case we need to replicate input data set among the all processes which are part of that particular you can say the process or the computation. Okay, because different processes will work on a different processor. Okay, they can execute concurrently also, if you see that. So if each process having that input data item set, okay, they can execute the independently there. Okay, means there will be no data dependency among the tasks in that case. And if the database is partitioned across processes as well, each task first computes partial counts. These counts are then aggregated at the appropriate task. Yeah, because even though database is partitioned across processes, means data input data set is available in each process, then also subtask will use that data set or items from that data set and perform the intermediate computation also, and that result may be utilized for the you can say the next computation by the another task in that particular process. Okay, and final result may be considered as aggregate of these different computations. So in case of the, we have seen just output data computation in previous example, output data decomposition. These 2 examples we have seen, matrix multiplication, then we have seen the you can say the this one database of transactions, that is input data, that is item sets in a database of transactions. So these 2 examples we have seen on output data decomposition from data decomposition approach. Then in same up, you can say the technique, data decomposition technique. Another you can say the sub technique you can consider here, input data partitioning. Okay, we have discussed about the output data partitioning or the decomposition. Now similarly you can perform the input decomposition also, and generally this is applicable if each output can be naturally computed as a function of the input data, if you see there. And in this case, in many cases it is only natural decomposition, because the output is not clearly known a priori. That is the problem of finding the minimum in a list or sorting a given list. Okay, for such type of problem you can apply the input data decomposition. Okay, where output is a function of the input, and if you see there, output is not clearly known a priori. Okay, and such type of examples are there. A problem of finding the minimum number in a given list or sorting a given list of numbers, if you see that. Then in this case, a task is associated with each input data partition. Yeah, you are partitioning the input data into different subtasks there. So each subtask will be considered as a separate task there. The task performs as much of the computation with its part of the data, and subsequent processing combines these partial results. Yeah. So subtask will perform their individual computation, and that partial result may be combined at last, if you see there, to get the final result of the computation. So this is the working, you can say, the mechanism of the input data decomposition or partitioning here. So we'll see example of the input data partitioning. Same example we can take here, which we have considered for the output data, you can say the decomposition. Okay, so in this current example, in the database counting example, the input can be partitioned here. Okay, and this induces a task decomposition in which each task generates partial counts for all item sets, and these are combined subsequently for aggregate count. That is the each subtask, okay, which are assigned to the input data, which are partitioned into multiple number of subtasks. Okay, their computational result or partial count will be considered for the final result, means their aggregate or the combined value will be considered for the final result. That is nothing but, in our current example, item set frequency counts, if you see there. So if you see there, here we are partitioning the transactions, because input item set here is nothing but the database transactions, if you see there. So there are total 10 database transactions we have taken into consideration, or 10 sets, if you see there, and out of them, first 5 are assigned to task 1, and next 5 are assigned to task 2, if you see there. Okay, total 10 you can say the input database transactions are there. So out of them, 5 are on task 1 and next 5 are on task 2, if you see there. Item sets are you can say the kept same here, and their item set frequency is also, you can say, we have not changed here. You see, our recording is in progress. Not. Am I audible to all?
Yes, sir.
Yes, sir.
Okay. A minute. I will just see our recording is in progress.
It is in progress, sir.
Okay, no problem. Okay. Sorry. Okay, I need to open it again. Okay, then we are talking about the input data decomposition or partitioning here. If you see there, so we have decomposed our input data set, that is the database transactions, into two sets here in current example. Okay, and we have not decomposed that is the in item set or the output data set like the item set frequency in this current example. Okay, so you can observe this current slide. This is showing the input data partitioning, and if you see the earlier example, that is showing the you can say the output data decomposition. So if you see that this is the output data decomposition example, same example, task 1 having the 10 number of records and task 2 having the 10 number of input records. That is not decomposed, only the output decomposition is taking place here. That is the item set frequency and item sets only. Item sets are first 4 are assigned to task 1 and next 4 on task 2 in the output data decomposition. But database transactions, this is the input data set or item set, that is not decomposed in this example. But okay, so in
Sir, we cannot hear you. Sir, we cannot hear you. Is there any problem in mic?
hello, can you listen now?
Yes, sir. Now we can
Yes,
hear
sir.
you.
Yes, sir.
So have you okay, so it was audible when I explained this current example, input data partitioning?
No, sir.
No, sir. Yes, sir. Input data partitioning example you were just starting, sir.
But,
Okay,
yeah, it was when began it only the sound was gone at that time only, Nitish.
okay, no
Yes,
problem.
yes.
Because yeah, I will explain it again, because we have taken same example which we have taken in earlier, that is the output data decomposition, that is the database transaction item sets, if you see there. So in current example, that is the input data decomposition, we have decomposed or partitioned only the input transaction item sets here only. If you see there, total 10 items are there. So first 5 are allocated to task 1 and next 5 are allocated to the task 2 there, if you see there, or assigned to the task 2 there. So we have partitioned or the decomposed only the input data items here, or the item sets, not that is the actual you can say the item set frequency. This is nothing but the output data we are considering there, like the previous example. While in case of the previous example, if you see there, we have not decomposed the input data set there, if you see there. So same number of items are in case of task 1 and task 2 of the input database transactions, that is 10 per task. If you see there, those tasks, that particular item sets from inputs are replicated, okay, which are part of two tasks there. Whereas as far as the item sets are concerned and their item set frequency count is concerned, this is nothing but the part of output, okay, that is decomposed here. In case of the output data decomposition, that is the we have partition or decomposed item sets into 4 different you can say the parts. That is, first 4 parts are assigned to the task 1 and next 4 parts are assigned to the task 2, and we are calculating or those tasks are computing the their item set frequency count also. That is ABC in case of task 1 having the count 1 because it is only the part of first item set from the input ABC. Then D count is 3 because it is the part of you can say second item, then fourth item, and then it is also the part of the ninth item also, if you see there. That's why its total count is 3. CFG 0, AE 2 again likewise. Similarly, in case of task 2, CD count is 1 because it is part of only the you see there 7th item, I think, from task 2, and decay count is 2 similarly because decay is the part of item number 2, and if you see there again item number 9, if you see there, that's why its count is 2 there. BCF count is 0, CDK count is also 0. This sequence is not present in any one input item data set, if you see there. Okay, so here decomposition is only on output data, not input data. 10 items are there from the database transaction in both tasks. Okay, only we have decomposed here output data. Similarly, in our current example, we are not touching the output data, that is item sets and item set frequency count. We are just decomposing the input data set, that is first 5 data items are given or assigned to task 1 and next 5 to the task 2, if you see there, and accordingly their frequency count will change here. That is ABC 1 in case of task 1 and ABC 0 in case of task 2. Likewise, if you see that, because ABC only is the part of first item set, and that is assigned to task 1, and it is not present, this sequence is not present in item set number 6 to 10, that is part of task 2, if you see there. Okay, similarly you can see the count for the remaining item sets also there, that will change accordingly. So this is the input data partitioning, and then am I audible now?
Yes, sir, you are audible.
Okay, so it is also possible to decompose the items, okay, using the both approaches at a time, that is the input decomposition and output decomposition. So we have taken same example here, that is the database transactions, if you see there. So here same input data decomposition is performed on the input data set of the database transactions. That is, the 5 are assigned to first 5 are assigned to the task 1 and task 2. That is the you can say the input data decomposition, and next 5 are assigned to the task 3 and task 4 respectively, as far as the input data decomposition is concerned. And if you see there, as far as item sets and item set frequency count is concerned, we have divided it into 2 parts. That is, the first 5 item sets are assigned for task 1 and task 3, if you see there, and next 4 are assigned to the task 2 and task 4. Okay, if you see there, and accordingly you can perform the computation, and you will get the final item set frequency count there. For example, in case of task 1, frequency count ABC will be 1, D will be 2, CFG 0, AE will be 1. Okay, and similarly in case of task 2, frequency of CD will be 0, DK 1, DCF 0, CDK 0, likewise. Okay, similarly you can compute for the task 3 and task 4. Okay, so intermediate computation will be performed by the task 1, 2, 3, 4, and you will get the final result, that is nothing but the aggregate or combining the results of all these computations, if you see there. So this is the way that is you can perform the input as well as output decomposition at a time, if you see there. Earlier we have seen the only example of the output data decomposition, then we have seen the input data decomposition, and the current example showing the combination of both input as well as output data decomposition. So in examination question might be there, what is data decomposition? Explain the output data decomposition with the suitable example. So you can take the example of the matrix multiplication or the you can show this database transactions. Similarly for the input decomposition or the combination of input and output data decomposition. This is not too difficult. If you understand once, you will not forget, I think. So under the same topic, that is the data decomposition, another approach is also possible, that is intermediate data decomposition or the partitioning. So computation can often be viewed as a sequence of transformation from the input to the output data. So apart from input data and output data, actual output data, so whatever you can say transformations or computations are taking place, that can be represented in the form of the intermediate data, and that data can be partitioned or decomposed. And how it is possible, we will see that with the help of one example, and this is beneficial to use one of the intermediate stages as a basis for decomposition. Okay, so this example represented in current slide, this is nothing but the multiplication of the two matrices, again dense matrix multiplication. So in this example, this is nothing but the intermediate result. Okay, that is you are showing first column of the first matrix and first row of the so you can say the second matrix, because these are the intermediate computations, those are taking place, and resultant matrix will be there. You can say D111, that is representing that is you can see a first element of the first column, if you see there, and you can yes, for first matrix that will be multiplied with the first element of the first row of the second matrix. Okay, their multiplication will be stored where, in case of D11. Okay, if you see there, and yes, this is right. Similarly for second position element D121, D112, D122, that will be perform there. Okay. Then say in case of the second column of the first matrix and the second row of the second matrix, again you will get the another intermediate matrix, that is D211, then D221 and D21, D222. These are the intermediate results of the computation. If you see there, then you can add these two sub matrices there. If you see there, and we will get the resultant matrix, that is C11. So C11 is nothing but the addition of D11 and D211 elements of these two intermediate matrices. C12 addition of D112 and D212. Similarly, C21, this addition of D121 and D221, and C22 is nothing but the addition of D122 and D222. You can see there. So in this way, we will get the resultant matrix. So here, two intermediate partitions we have made there to get the resultant matrix C. If you see there, okay. So this is called as the intermediate data partitioning. If you see there, and this first, you can say the partition may be assigned to one task and another one for another task. If you see there, and the resultant will be assigned to another third task likewise. If you see there. So this is the example of the intermediate data partitioning. Then another example is also shown here, the intermediate data decomposition. And if you see there, in this current example, decomposition of intermediate data structure leads to the following decomposition. In step 1, 8 decomposition, and in second step, 4 number of task decompositions will be there. If you see that. Stage 1, if you see there, D112, then D112, D122, D122, likewise. The final row is there, D222, D222, likewise. If you see there. So in second stage, if you see there, first 4 elements are considered as a separate, you can say the task or the matrix there. And next 4 elements are taken as a next matrix there. And addition is performed there, if you see there, to get the resultant matrix C, C11, C12, C21, C22. Then how you can say the decomposition is performed there. If you see the task 1 or task 01, how D111 is computed. D11 is nothing but the equal to A11 into B11. Task 2, T211. If you see there, where is this one? D211. This is actually the third element, right now, from the our stage 1 resultant matrix, third element of the first column. If you see that, so this will be nothing but the D11 equal to A12 into B21, and so on. If you see that, so in this way, we'll get the step-by-step computation. Those are assigned to the different tasks, and finally we are combining those tasks. For example, if you see the task number 9, we are combining this sub task, the C11 equal to D111, okay, which is already computed, plus D211 to get the C11, and C12 we are adding D112 plus D212, you see. And for task 11, C21, that is nothing but the addition of D121 plus D221, and task 12 is nothing but the C22, that is the second element of your second row of the resultant matrix C. You see there, C22 equal to D122 plus D222. So in this way, you can say the intermediate decomposition of tasks taking place there. If you see there, means you are decomposing data among the different tasks there, and finally you are combining its result also to get the final result. If you see there, so this is the example of intermediate data partitioning. So about the data decomposition, we have seen the example of the output data decomposition, input data decomposition, or a combination of input and output data decomposition. Then we have seen the intermediate data decomposition also. If you see that one example is also shown here, that is based on the task dependency graph, how we can represent the intermediate data partitioning there. If you see there, that is shown here 1 2, then you will get result like 9. The task dependency graph for the decomposition into 12 tasks is shown in this particular example. What is timing now? It is 12:26. So we should continue, or we should stop here today, because here we have finished data decomposition techniques, because data decomposition techniques are divided into if you see there 4 subtypes, like the input data decomposition, output data decomposition, then combination of input and output data decomposition, and last one we have seen the intermediate data decomposition. Okay, so it is the, you can say, somewhat a large topic if you see. And then today we'll see only the owner computes rule, and we'll stop here. The owner compute rule is generally states that the process assigned a particular data item is responsible for all computation associated with it. You see that, yeah, because we have already discussed process is nothing but the either a parallel program or parallel algorithm or parallel computational API. We have already discussed. So if data items, okay, or are already assigned to that process, means whatever tasks are part of that process, okay, those will utilize that data. Okay, means there will be no you can say the data dependency while executing that particular set of tasks, and which are part of that particular process in this case, if you see that. So process is responsible for all computation associated with it, because process is also not allow any one task to access data from the other process. Okay, because data dependency problem is not there. So in the case of input data decomposition, the owner computes rule implies that all computations that use the input data are performed by the process. Yeah. So as per the owner compute rule, if in case of the input data decomposition, if you see there, if input data items or item sets are already available with the process, okay, so in that case, all computations will be performed by the that process only to which that data set is assigned. If you see there, because all data required to complete the execution of the respective tasks, okay, by that process are already available with that particular process. If you see, that's why there is no dependency with other task or task from other process, if you see. So in the case of output data decomposition, the owner compute rule implies that the output is computed by the process to which the output data is assigned. But in case of the output data decomposition, okay, so computation will be performed by that process, okay, which will utilize the data, if you see there, that is produced by the current process, if you see there. So this is showing the data dependency, because data produced by the one process may be used by the another process in that case. So which process will use that data, okay, that process will responsible for this particular computation in case of the output data decomposition. If you see that, in case of input data decomposition, the process which are having that data, okay, only responsible. But in case of output data decomposition, the process which will utilize that output that is produced by the current process that process is responsible to complete the computation. Okay, if you say so, this is the owner computes rule. If you say that, sometime question might be there. What is owner compute rule? Explain with suitable example. Likewise. So today we'll stop here, and in next lecture we'll discuss about the exploratory decomposition and speculative decomposition technique. So I think we'll stop here. Thank you to all. And how many students present? The strength is not good today also. 35 students only. Earlier there were around 53 students. Okay, I will just check our recording whether it is, and I will stop recording.